Jiri Krepel.
Thank you. I'm coming from Switzerland, from Advanced Nuclear System Group of Polish Institute. And I don't like accelerators so much. Okay, I have also a disclaimer as the other speakers. First disclaimer is typically I try to pass too many messages. And the second disclaimer is all what I'm presenting here is purely from neutronic perspective. Nothing else than neutronics, yes? So, but at the beginning I have a few slides with basic data. So we speak about uranium and thorium cycle. So how much we have? Okay, there are two studies which you can find. One is saying we have 2 times more thorium, second is saying we have 4 times more thorium. But actually if you look on the half-lives, it sounds like logical because the half-life of thorium is a little bit longer. But the reserve itself, at least according to the data I found, are more or less comparable. Furthermore, there are some like 3 million tons already mined for uranium, and there is like more than 1 million tons left over from enrichment process. So I would say, at minimum, this is a draw. So argument with reserves, it's not valid for any of these two. From neutronic perspective, they are not fissile, but the fission barrier is lower for uranium. So as a matter of fact, you can fission up to 10% of uranium directly without transmuting it, and only 3% of thorium. Another thing, you can transmute them to the fissile elements, and in case of thorium, you transmute through neptunium, which has 1 order longer half-life. So as a matter of fact, it can eat neutrons, and it can cause proliferation risks. And last bullet, uranium-8 has a fissile brother. Yes, so from this perspective, uranium-8 itself is slightly better than thorium. But to have the full story, we must look on the transmutation products, so on plutonium-9 and uranium-3. They are not natural, they have different half-lives, but for those of you who like a geo-reactor, it is very important to say that plutonium-9 is decaying to uranium-5. It's not the case here. There is nothing fissile as a decay product. We have plutonium. We are producing yearly 70 tons. We have something cumulated. We have something reprocessed. There are maybe 2 tons of uranium-3 available somewhere in US. I'm not sure. So from that perspective, yes, if we need plutonium, we have it. I didn't include weapon-grade plutonium, but probably. Yes, they are both fissile, but now we should be honest, uranium-3 is better. In both in thermal or fast spectrum, uranium-3 has 90% fission chance. For plutonium, it's 83 in fast, which is quite comparable, but only 62 in thermal spectrum. If you invert it, if you look on the capture probability, it's 10% here for both systems, and twice or 4 times more for plutonium. So this is the biggest weakness of plutonium. The biggest strength of plutonium is you have 2.9 neutrons per fission, whereas you have only 2.5 for uranium-3. If you subtract now 2 neutrons, which you need for chain reaction and for breeding, it looks like this. So plutonium is up to twice better than uranium. So again, this is almost a draw, but it has implications. So now the title mentioned also MSR, so what I put here is what is MSR for me? It is hardly readable from back, but let's say there is a marriage of graphite and fluoride salts, so this is one category. Then there are homogeneous fast reactors where there is empty cavity filled by salt, and then there are the other concepts. Yes, it's my personal classification. In graphite and fluoride salts, there is also solid fuel, but I would not say that this is a molten salt reactor. It's more like molten salt cooled. And the liquid fuel you can design as you wish, burner, converter, breeder. In the homogeneous fast reactors, we have fluoride and chloride salts. You can do burner, converter, breeder, and fluorides. Nobody's proposing burner or converter in chlorides because they are so good that you propose rather breeder or breed and burn system. And there are other concepts, so other moderators, assuming that they are compatible with the salt, or let's say subcritical reactors, I'm not sure now, because I remember from my semester work from 1998 that there was also fast ATV version of Charles Booman, but I'm not sure anymore. Nevertheless, there is fast or thermal subcritical MSR. And okay, then you have typically chlorides with heterogeneous core, so there is structural materials or other coolant in the core. I excluded them from my study, and they were addressed this morning by Mr. Takashi, so he told you probably enough. Yes. So if you look on thorium and uranium cycle, you should exclusively look on breeders, or let's say breed and burn, for the comparison. So this is what we looked on. And the way how to compare was one study of comparing 16 reactors, not only MSR, other study looking for, let's say, MSR combinations, possible salts and moderators. And we looked on how good they are in equilibrium cycle and how to reach the equilibrium. Now, this is a very crucial slide for the rest of the presentation. So what is the equilibrium in the sense of this presentation? If you fixed all the fuel parameters, inclusive power, you don't care about criticality or subcriticality, you fix the power, then the reactor, after a constant operation, will converge to fixed fuel composition, which will depend on what you are filling, and which will also depend on the neutron spectrum of the system. The neutron spectrum itself will be mainly determined by scattering material presence, like moderator or not. And these two together gives you the final equilibrium reactivity. Yes, so whatever system you give me, I will try to fix the fuel cycle and check how much reactivity I get. And the reactivity can be used to say what is the performance of the system. Do we have excess reactivity? Can we breed? Or don't we have? Yes? So using this, we compared 16 different reactors. I will not introduce them one by one, but some of them, yes, there is salt-cooled, FHR, pebble bed reactor, or HDR, helium-cooled. There are 2 graphite cases with Fly-B and Fly-salt, and there are 4 fast reactors with 2 with fluoride salts and 2 with chloride salts. The last one is very hypothetical. It's actinide chloride, so there is no eutectic. It's very high melting temperature, but it's like an ultimate case for comparison. So, and this is the result. You can conclude what we already know, that thorium can breed in thermal spectrum in some reactors. Plutonium is better in fast reactors. If you look on the MSR reactors, you see graphite works only in thorium cycle, fluoride have equal performance in both cycle, and chlorides provide the highest reactivity excess in both cycle. And especially here, the reactivity excess is so high that you can do breed and burn. Once again, I'm trying to pass too many messages, so what I did, I tried to break down this result to components to understand why it is like this. So here is one slide with equations, sorry for that, but you can break down the reactivity to 3 major components. It's excess of neutrons, it's a bonus from fertile, which is like direct fission of the fertile and end-to-end reaction on the fertile, and then there is a capture of other materials like actinides and structural materials. And if you look on these 3 components, you may understand more how these 2 cycles works. For those who wants to see how it was derived, it is here. And let's look on the components. First component, excess of neutrons. Surprising result, in thorium cycle, you have 2.5 neutrons, whatever spectrum you have, because the equilibrium composition compensates for any hardening or softening of the spectrum. So even if you have very hard spectrum, there are only 2.5 neutrons. So to choose hard spectrum to have more neutrons seems that doesn't work. In plutonium cycle, you have 2.9 neutrons, no matter the spectrum. So if you take just these 2 values, the hypothetical excess reactivity is 31,000 ppm in uranium-plutonium cycle and 20,000 in thorium cycle. Quite big difference. The second term is bonus from fertile. So we speak about direct fission and end-to-end. It's up to 4% in thorium cycle and it's up to 15% in uranium cycle. So again, uranium cycle is better, factor of 2.5. The third component, and you can guess, thorium cycle should be better to compensate. So the parasitic capture of actinides is up to 20% in thorium cycle in fast spectrum and up to 40% in thermal spectrum. If you compare with plutonium, it's 30% in fast reactors, which is kind of comparable, but up to 120% in thermal. Another message from this picture is, if you look on the fluorides fast reactor, it's called fast reactor, but from this perspective, the performance is perfectly thermal. Yes, so the fuel composition is so that the captures of actinides are more or less acting as a thermal system. So now if you put these three components together again, you get the original chart, this time in reactivity form, before it was multiplication factor. So now you see that, okay, there can be thorium fast reactors, there can be thermal thorium reactors, there is less neutrons, but also less parasitic capture in thorium cycle. In uranium cycle, okay, there is more neutrons, more excess, but then whenever you soften the spectrum, you start to eat these neutrons very much. Yes, and around fluoride salt, you are passing through the edge where you cannot breathe anymore. So I call it myself that thorium cycle has high efficiency and uranium cycle has high economy. Before I leave this 16 reactor study, there is one more slide. We also looked on the migration area. You can imagine it as a transparency for the neutrons of the core. The more transparent you are, the more the neutrons are leaking from the core. And the outcome is very interesting. The less transparent, the least transparent are the fluoride salts, the fast fluoride salt reactor. And it is basically because of the big scattering peaks of lithium and fluorine, and because of their quite low mass, so they are more or less moderating to a certain extent. Second is graphite, and the biggest transparency you can find for chlorides, because there is no scattering resonance peak, and the mass of chlorine itself is higher. So this has consequences to the core size. So now, okay, I addressed only graphite moderated MSR, so let's look on other moderators and other salts. So we pick up 5 salts, Fly, Flyb, Flina, Fnac, Fnabi. And it's a hypothetical study. So let's take beryllium, beryllium oxide, graphite, heavy water, normal water, and zirconium hydride without any cladding. Just let's see. Oh, and to explain, each of this chart represents, I don't know, several hundreds of calculations, and you change the salt share in the core and channel radius in the core, yes? So what you can see is that Fly is the best salt, that beryllium and heavy water is the best moderator, hydrogen doesn't work. Okay, we don't have liquid hydrogen moderator, but we have zirconium hydride and normal water. None of them works. And graphite is not so breathtaking, but is the only one compatible, because beryllium and heavy water will need cladding. So we assess the cladding impact, looking on alloy, stainless steel, and silicon carbide. Silicon carbide seems to work. It's miraculous. And making a joke, if there is still a wealthy man in this room not having an MSR startup, I propose, let's do together a startup. We can do heavy water boiling, thermal thorium MSR. Okay. After that, we looked also on the fast reactors because they are more promising. So what we did, we checked 8 salts, 5 fluorides, 3 chlorides, and look on the performance in thorium cycle. The conclusion is that enriched chlorine has the best performance for thorium cycle. The best from fluoride salts is Fly, so the salt used in MSFR system. Then you do this, they did the same study in uranium-plutonium cycle. More or less there are 5 salts which can somehow work. Again, enriched chlorine is the best. And there are 3 almost equally performing fluoride salts. But I have two disclaimers here. This is for ENDFB70 library. The capture cross-section of chlorine 35 may have been reduced, so the performance of natural chlorine may be better. But anyway, it is working in uranium-plutonium cycle. And here, this is theoretically working, but you must take care about plutonium trifluoride solubility, which is not so obvious that it's possible to run this fuel cycle. So another parameter, we speak about thorium, which is miraculous. So let's have a look on radiotoxicity comparison between these two cycles. So what we did, we compare 1 kilo of equilibrium fuel for both cycles. So 1 to 1. We didn't care about how you reprocess, recycle, but we compare 1 kilo against 1 kilo. And the outcome is, yes, thorium is better, factor of 5 to 50 better. But at certain moment, plutonium cycle becomes better again, because there is some delay decay chain, and this is logarithmic anyway. But disclaimer, this is 1 against 1 kilo. If you design your cycle, for instance, uranium cycle may allow you to reprocess fuel with higher burnup, or thorium cycle may allow you to reprocess it with higher efficiency, who knows? So the outcome to the claim, who is better, will depend on your system. So saying that thorium is always better, it's not true. Yes? So I have 3 more messages to pass, and I have still some time. First one is the core size. To compare it, there are 3 typical fast reactors, lead, sodium, and gas-cooled, and molten salt breeder reactor designed for Anchorage to give you the size feeling. Then the fluoride salt reactor, so this is a minimal critical core size to breed with 1 meter of Hastelloy reflector. Yes, so the fluorides reactors are almost the same for both cycles. Yes, slightly bigger for uranium-plutonium cycle than for thorium cycle. For chlorides, it's the opposite. The thorium cycle is much bigger than the uranium-plutonium cycle, which is comparable with the previous 2. So again, it's hard to conclude what is better, if thorium or plutonium, but it's one other parameter which we compared. Then there is the breed and burn option, which obviously works only with this enriched 37 chlorine salt at the moment with this library. And I want to just say here that there is a difference in the breed and burn cycle in solid fuel reactors and liquid fuel reactors. So in solid fuel reactors, you load assembly without any fissile, just with fertile material, and at the end you unload the highest burn-up assembly from your reactor. In liquid fuel, you have no chance to remove highest burn-up assembly, because you can only remove average fuel, because everything is homogenized. The only way how to a little bit improve is like include more liquids, more, let's say 2-3 different fluids. Then you may improve this, then you may also reduce the size of the core. And comparison of the thorium and uranium cycle. So in thorium cycle, it's practically impossible to run breed and burn. You can mix the cycles, half-half is the purple line, then it may be possible. But uranium alone is better, and the more uranium you manage to dissolve in your salt, the better you are. Of course, you should care about what salt you obtain this way, and this has impact also on the size. Yes, so the breed and burn reactor can be relatively big, but also relatively compact. Yes, but the most compact design here, it's a salt which probably is highly corrosive. Okay. Practically the last message, the transition to the equilibrium. So we have 5 major fissile materials existing. One is reactor-grade plutonium. I would say we have medium availability and medium proliferation risk. Then there is low enriched uranium with high availability and medium proliferation risk. Low enriched, sorry, and high enriched uranium with also high availability but high proliferation risk. Uranium-3 with low availability and high proliferation risk. and weapon-grade plutonium with medium availability and high proliferation risk. So if you are a non-power country, like EU, for instance, you have only 2 materials. So it's a reactor-grade plutonium or low-enriched uranium. And now, using these 2 materials to start the 2 cycles, it's diametrically different. So if you look on plutonium cycle, it's quite natural. If you use the reactor-grade plutonium with depleted uranium, you are almost at equilibrium, because this is more or less your equilibrium composition, yes? If you use enriched uranium, you will just convert this uranium to plutonium during your operation first few years, and that's it. In thorium cycle, if you want to have the same fissile content, you more or less need to mix the cycle. So you will have uranium-8 with thorium in the system, because you are limited to 20% enrichment. So you must put uranium-8 into your thorium reactor at the beginning. Or you need to put plutonium to your thorium system. But both of them are perturbation. Both of them are not in the equilibrium. So you need to care that your salt allows this. And to illustrate this, I prepared a chart which can look familiar for chemicists, but it's just plotting neutronic results. So the equilibrium composition of a thorium cycle here is for fluoride salts and here for chlorides. And this is the equilibrium for chloride salts, but in the uranium-plutonium cycle. And now the biggest question is how to start the molten salt fast reactor in thorium cycle, because if you use low-enriched uranium, you need to pass through this curve. So at a certain moment, you will have a lot of plutonium in the system. If you use only plutonium, you start from very high concentration, which is also above the solubility. So the official way how to start it nowadays is find a mixture of them and use the mixture. So we did parametric study, so you pick up one mixture and say, okay, this is my mixture, let's start it. For thorium cycle in chlorides, it's the same curve, but you don't mind because the solubility of plutonium is high. And for the uranium-plutonium cycle in chlorides, you almost don't see the transition in plutonium case because it's this move. And this is for the enriched uranium. So that was the last message. I would just try to summarize a little bit. So the reserve itself, there should not be an argument for one or the other element, and we should be really happy that we have both. Thanks God for the supernova, yes, I would say. The features of these 2 elements, uranium-8 and thorium-2, I would say uranium is slightly better because of the direct fission, because of no protactinium, and because of the fissile brother. If you compare plutonium-9 with uranium-3, it's slightly more complicated because plutonium gives you more neutrons, but also eats more neutrons. Thorium gives you less neutrons, but in equilibrium cycle also eat less neutrons. So you need to decide what is better for you. In thermal spectrum, you can breed only with thorium. In fast spectrum, in both. Breed and burn at the same time is possible only in plutonium cycle, in uranium-plutonium cycle. Now, the radiotoxicity is questionable, but if you really compare 1 to 1 kilo of the waste, plutonium cycle has initially higher radiotoxicity, factor of 5 to 50. The core size, on the other hand, if you go for chlorides, it's smaller in uranium-plutonium cycle. For thorium and chloride salts, it's quite big, the core size. For fluorides, uranium-plutonium cycle provides you slightly bigger reactor size. The transition to equilibrium in fluorides is smooth for plutonium cycle and challenging for thorium cycle. But smooth here is with the disclaimer if possible. So if your final equilibrium state has sufficient solubility of plutonium, then you can find smooth transition. And the transition in chloride fast reactor is quite smooth for both of them.
So very, very nice study, especially the phase diagram, I love that. But you calculate this from K infinite, so if you were to take the size of the reactor into account, Did that influence a lot? I mean, between a so-called fast reactor and a fast salt reactor, there's a huge difference in the leakage path of neutrons between fissions, and that should influence the leakage.
Okay, I didn't go in details to say what assumptions we use for different studies. So the first 16 reactor comparison was infinite lattice, no fission products. The next study of moderated and fast reactors was already including fission products, but it was infinite lattice. And this transition, this was already done for finite, so for realistic core size. Yes, but you are right. Therefore, I showed the chart with the migration area to give you the feeling how they differ. Yes, and especially chlorides are really transparent. So, yeah.
When you're looking at this nice breeding cycle that's never really been done, but everybody want to do it. Before we are there, we probably need some burning cycles. And this is the only time at this conference I will defend thorium. But for this, mixing thorium into enriched uranium can extend the burning length of current per unit uranium. Is there any way to take this into account in this slide?
Right, what you are saying. Thorium has the advantage that its daughter product, uranium-3, has quite low capture. So more or less in dynamic system, at best, if you profit from the plutonium feature, so if you mix plutonium with thorium, you create a system which is at the beginning profiting from many neutrons, and later profits from uranium-3, which has not so high parasitic capture. So yes, indeed, you can create some cycles where you profit from plutonium cycle and profit from thorium as semi-inert matrix. Yes, that's true. But this is for, as you said, for burners. If you have something you want to burn, yes. I can do a similar presentation for if you want to burn, yes.
But we want to burn stuff for the next 100 years or so.
It depends on the perspective. I see these materials as assets. I don't see anything we need to burn immediately. Yes, if you have problem with weapon-grade plutonium, just mix it with reactor-grade plutonium.
No, I'm not only burning plutonium, I also enriched uranium.
Can you repeat your question? We need to burn enriched uranium?
Burning enriched uranium.
Yes.
You can extend the amount of burn-up you can get higher burn-up by mixing thorium into.
I think there was a clear conclusion on Monday in the plenary that whenever you want to burn, don't put thorium in your system, because thorium will just push your enrichment up, and finally, if you calculate how much you utilize from natural materials, it will be maybe even less than if you would rely on 5% enrichment instead of 10. So I don't want to speculate, but we did that calculation actually for HDR. Let's try to use thorium as an initial poison for initial core of HDR, and let's hope that we will increase materials utilization. It didn't work.
Maybe I just skipped it, I'm sorry, but at the beginning you said 2.5 for U3 and 2.9 for, but that's not true for fast systems.
That's perfectly true for fast systems.
I mean, if you have fast neutrons, you can get more than those.
That was exactly the surprise we obtained. I will try to get back to these slides. If you go to hard spectrum, chlorides have perfectly hard spectrum. You get from plutonium-9 more than 2.9. You get 3 something. Yes? But at the same time, let's say we are somewhere here, you are missing the components from plutonium-41, 42, which is present in equilibrium cycle in thermal reactor. And they compensate. So the equilibrium fuel composition compensates these effects. So therefore I said, if you look on equilibrium cycle, it's surprisingly flat. It's not an argument to get more neutrons. You don't get more neutrons. A very big surprise, actually.
Maybe, first of all, a compliment, a very nice exercise. You're talking about reprocessed plutonium. I mean
the mass. Yeah.
From the reprocessing plant. What about the reprocessed uranium? Okay, you could use this one, but this is not kilogram. You have this is several tons. Exercise for this one.
You can guess it. You can guess it. Sorry, it's too many clicks. But you can the previous slide. Yes, you can guess it from this. Look, we mined so far 3 million tons. Yes, and we are not capable to burn more than 1%. So if from these 3 million tons, one is left in the reprocessing facility, the other two should be left as a spent fuel somewhere. So yes. But once again, I did it just to say, don't argue with resources. Really, we should be happy for both. I mean.
How are you going to deal with all of spent fuel?
Sorry?
How are you going to deal with the spent fuel?
In closed fuel cycle, you don't speak much about spent fuel, you speak about reprocessing losses. Yes? And what we do nowadays with reprocessing losses, typically we vitrify it.
All right, any more? Otherwise, we thank Jiri again.